It's a pleasure to be here. So what I want to tell you is more or less a story about how I got into this business. I'm not making the assumption that everybody here is excited about integrals. Hopefully by the end of the talk, some of you will be. So I think that a better title for the talk was something like this. It took me a long time to answer this question correctly because when I started doing this, it's been a long time now, but at the beginning, I used to go to meetings and people would ask you, what do you do? You do algebra, you do topology, you do geometry. I would be embarrassed to say I compute integrals. So I'll say I do analysis, or I do number theory, I do this and that. And then one day I decided this is silly, this is what I like to do. So I have tenure, what do I care? So now this is what I do. And so I have a research project that I would like you to join me. What I want to do is I want to evaluate an integral. This is a calculus 2 on steroids. Is it called calculus 2 here? Integral calculus. So first of all, it all started with a graduate student. As I mentioned before, at tea time, Tulane has a pre-tenure leave. After 3 years, you pass a third-year review. You get 6 months off. So when we passed the third-year review, we went to Salt Lake City doing projects with somebody. When I got my PhD at Courant, I worked with Henry McKean on PDEs because I like the guy. As I was telling the graduate student before, a good advice is you choose the person you want to work with, then you choose the subject. So then I came back to one of those sabbaticals. I came back there and I had to teach a graduate course in analysis. And there was a graduate student there that was older. And at that time, I got my last paper on the business. It was about some kind of wave propagation on eggshells. These are the kind of things that I used to do, calcium waves and stuff like that. So then this graduate student told me he had a formula. Okay, so I was being polite. So what? And it was a very good coincidence because that was at the time that I started to learn Mathematica. Tulane has a free license for everybody. So if it's free, why not use it? And so this is the integral that will reappear. It's the integral of a quartic polynomial to a power. A is a parameter, real parameter bigger than -1, just for convergence. You'll see that I don't care very much about convergence. I'm Eulerian at the point of view, I'm before convergence. So I had no idea what he meant. He had a formula. And then I remember that in calculus, when I took calculus in Chile, not that year, 1650, after that. There's this formula called Wallace's formula that has it like this. This formula used to appear in calculus books. Then it was relegated to start exercises at the end of the chapter, and now in the new calculus book has disappeared. That's what we do now. So I knew nothing about integrals. And so I knew nothing what this guy was telling me. And I started asking about the student, who's a first-year student, slightly older. It turns out that he was an accountant working. He always wanted to do math. And his wife told him, look, just go to grad school. You're wasting your life. You're unhappy being an accountant. So he went to grad school. Lucky for me. So then his name was George Boros, and he told me that he could evaluate this integral. And I had no idea what he meant by it, and I had to give him good advice as his first year student, and I said, this is not serious. I told him, this is not serious mathematics. I was pompous and young, and I thought I knew something. So I tapped it into Mathematica to see what it is. And I told him, look, these people are very smart, they created this language, they can do everything you can. So you typed it, and to my surprise, Mathematica couldn't do it. I typed some numbers for A, some numbers for M. So if you plug in A equals 7 and M equals 500, Mathematica does it for a long time, computes, and gives you a number. But with parameters, it couldn't. That was 1997. I tried today again, still cannot do it. So Mathematica has not improved in this part. So I got curious. Why does this guy know how to do something that looks strange and complicated? So I got interested. So then it took me some time to realize that I was very wrong with my advice. So to be honest, I actually went to tell him that later on in life. As you know, I was wrong telling this advice. Thank God he ignored me. So he's a smart guy. So the question I want to tell you is, where do they come from? Okay. So this is a fast survey about where integrals come to your life. First of all, they come with areas and curves, right? This is the area of a circle, for example. And it's an interesting example to do in your calculus class, that you can prove that a circle of radius r is r squared times the area of a circle of radius 1. Scaling comes down directly by a change of variable there. So it's a nice, I think in physics courses they do it, but in math courses not. Here's another example, volumes of revolution. You can do the same trick, volume of spheres. When you take length of curves, they become more complicated, as you well know. For example, taking a simple conic, like an ellipse, you get these beautiful integrals that are called elliptic integrals for obvious reasons. And they're a subject close to my heart. And there's something called there, this will reappear again. The k that appears there is called the modulus, and this integral is called the complete elliptic integral of the second kind, and it's written as k of k. So there are integrals in that case. And these things were at the center of analysis in many problems in math and physics, 18th and 19th century. Okay? And these are examples of what are called the periods. It turns out that if you invert an integral, you get a anamorphic function on the plane, you get an elliptic function, and this integral is one of the periods. And the periods became a sophisticated subject these days. There's a beautiful survey paper by Tal Zagier on periods. Okay, that's an example where it appears. Again, I'm going to tell you the evolution of integration. In the middle of the 19th century, people started collecting these things. Right? So they were putting in little booklets. And there's a Dutch guy named Pierre de Haan who put a table in 1858. I own the reprinted version in 1857. And then he published a book how to do it. It's the best calculus book that I know. It's long and complicated. Then they publish errors, right? Every time you make a table, there are errors. And then somebody in 1881 studied things as an example. And then what happened, there were two Russians that came into the picture. Rizhik wrote a book on special functions, and he died in World War II. And so the book appeared in 1943, post-mortem. And then Grashnik was a younger one. They never met, obviously. Grashnik got the draft of the book, and they put it together. And there's a table that is the most used nowadays. It's called Grashnik Rizhik, or simply GNR. The 9th edition will appear in 2026. I was an engineer and undergraduate, because in Chile, when you finish high school, there were 3 things you could study only. That was the rule of parents. You either became a doctor, God forbid. My dad was a doctor. A lawyer, I would have been a lawyer, but in Chile you have to wear a tie if you go to law school, and that was out. The thinking of a 16-year-old doesn't change. You know? And then the third was to become an engineer, if you knew math. So I went to engineer school, and every engineer school there had a backpack with these tables. It was bad if you were a chemical engineer because you have to carry these integral tables plus this CRC table with things. So you break your back. Yeah.
This upcoming edition is going to be in print?
Yeah, the printed version will appear in 2026.
I'm surprised that they're still doing that.
I'll tell you who. Why surprised? Papers, it's good to read on paper sometimes.
No, I agree.
Thank you. Okay, so the question is how do integrals appear? They appear as interpolating functions. You take the sum of the n natural numbers, easy to compute, right? We'll teach you the first courses. Then when you multiply, you get a new function. And in math, it's very typical that when you have something new, you cheat by giving a name and then become something sort of known. These are factorials, right? So factorials is an interdiscrete function, because when you want something, when you go from the discrete to the continuous, you have to know how to extend. So is there a natural way to extend factorials, right? The answer is yes, if you're Euler, right? Euler came up with this formula for a new function called the gamma function. I think it was Laplace, who shift. Euler had the original presentation with an x to the n. Laplace said it's better to put an n minus 1, plus z minus 1. And that's what Laplace did. But the gamma notation is due to Euler. Okay, so this is a function that interpolates factorials. So there's integrals again. And there's the picture. This came out from most likely Wikipedia. That's what the graph of the gamma function is. It's a cool function. One of my favorite functions. The factorials you see come on the right, but then all these oscillations coming on the left. What is curious is that when you see this problem comes from taking these factorials, and you want to do something continuous. Why is number theory embedded in here? Right? This function belongs to number theorists, so they say. Right? So this is something. There's a number theory component here that is not clear at the very beginning, and this thing will reappear. So these are special values. For example, the gamma interpolates the integers, but gamma of 3/2 is root pi over 2. Surprising. Right? Feynman has a saying that said that you can judge if a person is a scientist if he knows the value of this. If he knows that the integral of minus minus x squared root pi, then it qualifies to be a scientist. Otherwise, it doesn't. He's more judgmental than I am. So that's the normal integral, okay? And this is the first question in every class in every country on the planet. The first question the students ask is, do you curve? And that's the curve, right? And then once at Tulane we have this undergraduate beginning year course. We do calculus 1 and calculus 2 together. We call it consolidated calculus. And I like to teach the honors class because these are kids from high school who think they know something. It's my job to tell them they don't, right? And once the first test was so easy that the grades were like from 90 to 100, so I curved. From 90 to 92 was an F, from 92 to 94 was a D, the average. They have no sense of humor when it comes to grades. They will accuse me to the dean. Yeah. Okay. So this is, I'm in the process of writing an undergraduate text for mixing functions in different ways. And so I had no funds at one point, so I called the dean's office and I said, look, I need some to help me judge the problems, are they hard, they're easy, check the problems and so on. So he said, look, we don't have any more money, but here's an idea, teach a 1-credit course, right? And the students, I had 2 students in mind, so 2 students will come and help me, they will get 1 credit, I will get my things checked. Win-win situation. The word spread, so every Tuesday we met, and there were 18 students. Wow. And there they are. We meet every Tuesday, and at Tulane, there's food for free if you know where to ask for it. So they were in charge of bringing the food on Tuesdays. Okay? And I will teach them some math and some integrals and some other things along the way. It was a lot of fun. Most of them graduated already. They're going to better things like medical school and childish things. Okay, so here's the quartic. This, remember the ends, this n0 is the integral with a quartic function. It's the integral of a quartic polynomial to a power. Okay, that's the only thing. And it turns out it's not hard to guess this part. You do 50 examples and you see a square root coming in, right? So you more or less can guess this piece, and then it's a polynomial, piece of that. Okay, and this polynomial will reappear in the talk. So this polynomial is a polynomial degree m. M is the index that appears in the integral. Let me write it down here maybe. So, okay. This part is not important. It's a polynomial, okay? And the coefficients are there. So then, that's the formula that George had. He showed me that formula. And now I was interested. So here's a formula for the polynomials he gave me. Right? He had this method, this horrendous triple sum. And is another good coincidence is I was learning how to use these very cool methods called WZ for Wilf and Zalberger. They were developing these automatic proofs and had to check things. So my first reaction was I sent this message to Doran. Doran is a friend of mine, so I said, look, what can your package do for this? And he sent me back a letter and says, nothing. So that became more interesting, right? It's like their powerful method cannot do anything. So that's the triple sum. I had no idea what to do with this. Right? What exactly do you tell a student who brings a formula like this? Okay, so here my original reaction was to compute some values. Right? To compute some values, and I said, look, I compute some values in Mathematica, and my observation was that they were positive. That was my contribution. I looked at the data and they were all positive. Right? But this here has an oscillating term. Right? So this thing is not a priori positive. It's not obviously positive, this sum. So I thought, George, you should prove that. That was my contribution. Find the proof. Yeah? So the kid was very, very powerful. It has a very interesting thing. So here's the proof he found. He found another formula for the coefficients, now without the -1, an interesting single sum. We went from triple sum with oscillating coefficients to a single sum with no -1s to the end. So I can prove now this is positive. That's staring. Okay? And I asked him, how do you prove that? And he proved it, he said, because you do an expansion. You do a Taylor series expansion of this double square root. And the integral that appears here is the coefficient of this double square root function in terms of C. So I sort of like, okay, no idea how he figured it out. And we wrote a paper, the paper appeared, was accepted. I had no idea how he thought of it. I talked to him years. How do you think? He said he had seen some papers on a manager, maybe he'll tell me. I think he read something in analysis, one of his expansions. There is a very nice book of Hardy called Pure Mathematics that actually has this expansion in two special cases. The case A equal 1 and the case with C equal A squared. No other cases. So I was intrigued about this, right? How did he think of that? I still don't know very well. Unfortunately, George passed away unexpectedly, so oops. Okay, there's the integral. And now I want to tell you some bad news. Bad news for me. So here's the integral, right? And then we had this polynomial, and we had an explicit formula, right? An explicit formula, and now I wanted to know things about this polynomial. What the coefficients are, we knew there were sums of binomial coefficients. I wanted to know what the zeros look like, how do the plots look like, and then are there recurrences, right? And there's no standard method to prove recurrences, but there's a very nice trick of Hermite. Hermite wrote a series of papers that now belongs to the basic of symbolic integration, of symbolic computation. All these things that are algebraic packages that appear in things like Mathematica that are based on theory developed by Hermite for a different reason. And Hermite has a technique to find recurrences, and we found this recurrence for the polynomials, for the integrals. Okay? So then there's a recurrence for the polynomials. Right? So then we start getting nice formulas, nice things. My fear was always these polynomials are known. People who make polynomials for a living, people who do orthogonal polynomials, people who do special functions, they must know these guys. That was my fear, right? I'm writing these papers, tempting students to work on these things because they were interesting problems. And in the back of my mind, there was always this fear that I should ask people who know. And no, they said, no, nobody sort of knew these things. So, really bad news now. So, we found an integral entry. This is the table that I mentioned before. The table is like a phone book. For those of you young people, phone book is a big book like that. So, it's the integral, that's the number, and it looks like this, right? It's an integral of a quadratic, but you make a change of variable, you can convert the quadratic to a quartic. There's the beta function, and there was a strange thing about 2 of 1. So we wrote a little paper on something that we have found, and the review was really fast and dramatically nasty. The guy says, anybody who knows anything about hypergeometric function can do this in 2 lines. I hope the referee is not in the room, but I didn't know what to do since I didn't know anything about hypergeometric functions. So one is either you abandon the project, and I was really interested now, or you learn about these funny functions. So it's like to learn about this function. And then this hypergeometric magic that allows you to convert these nasty formulas to our case to the polynomial piece of M of A that appears here is indeed one of these Jacobi polynomials. And I was depressed. There are several papers on these polynomials, and then they all become trivial because they're just formulas of Jacobi polynomials. And now I want to tell you what Jacobi polynomials are, right? This is a notation for Jacobi, piece of M alpha beta. I was very disappointed. Okay, so here's my one-page summary of Jacobi. There will be no test at the end of this talk. Yes. So Jacobis are exactly the following. You take your favorite weight. Since you're integrating from -1 to 1, it's natural to have a weight that vanishes at the boundary, linearly. So you put 1 minus x vanishing at 1, 1 plus x vanishing at -1, you put powers alpha and beta, you plug them in here, you do Gram-Schmidt, those are Jacobi. That's it. And people who know this business, they know lots of formulas. For example, there's an explicit definition here, like that. There are theorems that says that the zeros, because it's an orthogonal polynomial, must n distinct zeros all contained in the interval where the measure is. Okay? So the bad news was this. Okay, so I was curious about this, and then more confusion. So these Jacobi polynomials have these recurrences. They come from, this theorem says that polynomials are orthogonal if and only if satisfies recurrence of order 3. Theorem of Shihara from the 18somethings. So I had a recurrence. So what I did was to check my recurrence with the recurrence of Jacobi. Right? Now that I know that I'm so disappointed that I have to send a letter of apology to the editor of the journal, right? Saying essentially you referees don't look at don't know what they're doing. So I compare the recurrence that we had with the recurrence for Jacobi, and they didn't match. I was more confused. I said, what's going on here? So after a long time, it took me, it was one good day where I realized that we were saved. And the reason we were saved, because in all the theory, and this, they don't tell you this in the books on special functions. When you look at Jacobi polynomials like this, the alpha and the beta have to be independent of them. These three parameters have to be independent. And in our case, they're not. And so I was saved. At least it wasn't completely obvious what we had done. So I did the natural thing. I called somebody who knows about this stuff. So I called George Andrews, that by now I knew. And I said, look, this is the thing. Tell me a reference for Jacobi polynomials when the indices are linear. What are you talking about? These are not orthogonal. I said, but there has to be papers on that. It's a natural question. No, nothing. There's nothing in the literature. So I was happy. So here's the natural questions. George and I proved in 1999, using some theory of Schlegel, that this polynomial piece of m has no real zeros when m is even, and a single zero when it is odd. So the minimal number of zeros. You have a polynomial, the minimal number of zeros you have is the degree, depending on the parity of the degree, right? So the minimum. And then if you plot the zeros, they look like this. They converge to a lemniscate. So they look a picture like this, some round oval thing. I think this is 49, 50, and 51 like that. So for a long time, so this is 1999, for a long time I had this as a good thesis problem for a student. Especially because we had no idea what to do. Right? So I was looking for a student and nobody turned on and said, that doesn't look interesting. Okay? You're lost. And then I went to recruit students a long time, about 8 years ago. I went to Colombia, they invited me to give some talks, and I recruited some students, and this kid came, he's a grown man now. John Lopez Santander came to Tulane and worked for me, and he suggested some thesis problems, and I had mentioned this in passing. He said, I want to try that one. Okay, good. Brave man, I thought. And then he sold the thesis. I had a problem for about 30 years, I didn't know what to do. And he defended in March, and the poor guy is now doing a postdoc in Manitoba where it's minus 40 degrees. I have two Colombian students that have graduated. One went to Finland for a postdoc, and the other one went to Manitoba. So I have a third one now. She made me promise that if she, by miracle she finishes, she wants a postdoc in a park where it's not that weather. I said, okay, we'll try. So it was really interesting because the thesis is based on something called Riemann-Hilbert methods. Riemann-Hilbert methods are methods in analysis. Essentially, they are asymptotic methods for how to discuss what happens to analytic curve, functions analytic on two sides of a curve. You take in the real line, for example, you take the real axis, you have an analytic function on top, analytic on the bottom, and then you want to know something in the middle. That's what. So Riemann-Hilbert is a generalization of that, and John masters these methods because we now today would hire Ken McLaughlin, who's one of the world experts in this Riemann-Hilbert methods, and he was looking for nice applications, and he became a co-advisor. Yeah. So the moral of this first part of my talk is it's possible to do cool math by computing integrals. Right? It's my revenge. Okay. So here's the general problem. I want to the following. This is my global problem. You have a function defined from an interval to a real line, and you want to know something about the interval. Anything. So there's the example done before. So this is the formula from the polynomials that I mentioned in passing. Here are the polynomials. You see the coefficients are very nice. These coefficients have very interesting properties. And since there are number theorists in the audience, we know everything about these coefficients from the point of view of two-adic properties. So I can tell you exactly the behavior of the sequence of numbers, what is the power of 2 that divides them? So for example, this 2, I take it out because it's just a power of 2, so I have to contribute another. There's a sum, a finite sum of binomial coefficients, and I can tell you exactly, if you graph it in Mathematica, you see these pictures that are sort of like little triangles typed. I can tell you exactly what the form are, how many peaks there are, when there is the folding. We know everything there is to know about the power of 2 of these polynomials. Nothing about 3 or more, right? Nothing about odd primes. Anything we tried, and we tried a lot and did a lot for this coefficient, for p equal 2, nothing worked for 3, not even 3. So I always say 2 is an odd prime. Okay, so I told you where else they appear. They appear in this strange expansion. That's where the polynomials appear. And then, okay. So looking at this, right, the strange appearance of the integral in terms of the double square root, an actual thing for me was to see where do double square roots appear somewhere else, right? Why do people care about double square roots? So I started looking around, I started looking for things, and then I found this formula in that table, right? I have a physical copy of Nash's intrinsic. There's a beautiful formula. You don't think it's beautiful, you have to change your taste. There's a, look, phi is a simple rational function. It's actually a Möbius transformation in x squared. Right? It's not work right. So there's a 2 square roots because there's 1 square root here and 1/2 there. That's what I was looking for. I want to know, unfortunately in this table, they don't tell you who put the problems there, right? And they don't tell you why they put them. This is not a random. Somebody sent an integral to the editor, and the editor likes it or not, and they put them there, but the information about why the problem was interesting disappears. And not every integral, you can send the integral of x to the n from 0 to 1 for n equal 1 to 100, you send to the editor will say no thank you. Right? So each problem has something. It's a beautiful formula, right? But it's incorrect. We discovered that it was incorrect because I thought these people had done numerical checks. I thought this is a decent table, they sell it to you, it's not cheap, right? Somebody must have done numerical checks, parameter studies, numerical checks to guarantee that what you're selling is correct. No, nobody, okay? So there are 2 interesting problems now, because you need to know now which is the function that you have to put on the right, on the left, that integrates to pi over 2 root 6. That we found by doing some hypergeometric magic. It's a 3 there. Somebody copied the formula and forgot that 3. It's a human endeavor, right? So it happens. Right? It took us about 5 years to find this 3, by the way, because we didn't know what to do. Right? And then we also know what is the correct right-hand side. It's ugly. It's a difference of 2 elliptic integrals, so they're not important. Okay. So you asked before, who does this, right? Who collects these integrals, right? So I complained so much about this problem. I complained about the fact that the integral was wrong. I complained about the fact that there's no database. I complained about the fact they don't tell you where the integrals come from, right? And they are so fed up with me complaining that they made me the editor. So I'm the editor now. So one of the editors had passed away, and Dan Zwillinger, who has this company in Massachusetts, said, look, you have to be the editor. So I said, okay, why not? So I'm the guy in charge now. So I'm trying to be more honest than before. We're going to create a database where the integrals have stories from behind. Evaluate an integral per se is not so cool, but there are stories from behind, right? They're really, okay, we'll see. Okay, so let me tell you about, okay, how long is this? I can talk for 2 months, huh? 450, okay. So, what is interesting is that you can use integrals to define functions, right? We do that in calculus. So you integrate, for example, from 1 to x t to the minus 1. And the reason why you integrate this one is because it's a nice formula for the exponent is not minus 1. And you tell the student you cannot divide by 0, it's illegal. So you create a new function. You have to actually justify that as a new function, right? Maybe the log of x is some really hyper-complicated formula with rational functions. And they have to give an argument. You have to prove, and there are interesting analytic proofs that log x is not rational. that are, in my opinion, more interesting proofs that are purely algebraic. Right? The purely algebraic proofs that log x is not rational. They're interesting to understand. And the reason why is that because one of the things that appeals to me in this thing about symbolic integration is that there's no analysis really. There's a little bit of asymptotics, but it's mostly algebra. All symbolic integration is mostly an algebraic endeavor that is hidden from the user. So there's a lot of interesting algebra hidden there. So, okay, here's a famous function, the gamma that I told you before. Then you can play the following game. There are interesting numbers that come out of these functions. For example, you take the derivative of gamma, I don't know why, and then you plug in 1 with a minus sign. And you get a number in analysis that nobody knows anything about. Right? It's the most complicated number, in my opinion, right now, because they're not even good algorithms to compute this Euler constant. When you want to compute 20,000 digits of this number, it's complicated. Much more complicated than E and pi. Okay, so the other thing you can do is you can combine them. So you can take this gamma, you can take log, why not, right? And then you raise to a power. That's how we play. Whenever we have a problem that appears as interesting, we think, okay, let's have 2 there. Let's change the 2 by an n. Let's see if we can say something. Most of the time we can't, but sometimes we can. So here's L1. L1 is not the L1 from analysis, it's just this L1 here. L1 is the integral from 0 to 1 of log gamma q, dq. That's a theorem of Euler that is a beautiful log square root of 2 pi. Okay? I had a collaborator from Chile who actually went to my same high school. It's a small town. This is interesting. He has a PhD in physics. I went, many years ago, I went to give a course in Chile, trying to get people in the math department to get interested in what I do. None of them were interested. Right? Because there are no theorems. You don't do any theorems. So then, this kid that was in the physics department, he was an experimental physicist. He says, this is really cool. He tells me, you don't care about the convergence. No, I said, of course not. And then we started working, and he was incredibly smart, right? So we got lots of work done together. And one of the things that we were working on something called Hurwitz zeta functions. The Hurwitz invented is a two-dimensional version of the Riemann zeta function that is important in quadratic fields, for example. And we got this formula. This formula came with a paper, 2002. This formula was buried into something else that we were interested in. And when the paper came out, I didn't like it so much. I didn't appreciate how cool this formula is. We appear in the middle somewhere, right? So what you do is you integrate from 0 to 1 log square. And you get this, okay? So you go from log to pi. L1 is here, so this L1 is equal to log of the square root of 2 pi. And I want to show you a game that I like.
Is squaring or is it composition?
L1
Like,
what is a number?
You're
What is a
squaring,
number?
You're squaring. log.
Like 2 times 2.
Yeah, okay. then,
Yeah. L1 is a number, there's no composition. L1 is this number here. So this L1 square means take this log and square it. Yeah? So that's the formula we
No,
have.
I meant in the integral of L2.
Oh, no, yeah, it's log gamma of x squared. Yeah,
Okay,
I understand.
okay,
Yeah,
okay,
yeah.
yeah.
No, the integral of log gamma is
Yeah,
much more complicated.
Yeah.
That you need to know number theory. Okay, so the answer that comes here involves this L1, right? So I wanna play the following game. What I want to do is to think about, take these numbers that appear, gamma, pi, L1, and so on, and think of them as taking the rational numbers, okay, and do an extension. Okay? So I take the rational numbers and I adjoin gamma. And I think of gamma as a variable. Okay? And I do the same thing. I take the rational numbers with gamma and I add pi, and so on. And then what you observe is that I'm gonna show you how to assign weights. So I'm gonna declare pi to be of weight 1. Pi is gonna be a variable now of weight 1. I want to convert this formula that smells of analysis into a formula in algebra. So this becomes a new variable, let's call it pi squared. So this is a variable squared. And so in order to match this with this, I'm going to assign gamma also weight 1. So it becomes weight 2, weight 2. Gamma became with weight 1, right? So this L1 better have weight 1. So the two pieces become weight 2. Okay, L1 is this, right? Pi has weight 1, so in my business of transforming numbers to variables, I should ignore the 2, the base field, so I ignore it. Ignore radicals and ignore logs. This is a very non-developed theorem, as you can see. So this gamma L1 becomes weight 2. This is also weight 2. This is weight 1, and here I have this ratio. Pi squared has weight 2. This has weight 1. So I have this and that giving weight -1. This guy here better have weight 3, gamma prime. Gamma 2 is pi squared, right? Because the 6 doesn't count. When I take derivatives, the weight should go up by 1. That's my rule. So this gamma prime of 2 becomes something weight 3. So I have 3 plus 1 is 4, minus 2 is 2. Again, weight 2. Here, same thing. Two derivatives go from weight 2 to 4. Subtract 2, you get 2 again. So this is a homogeneous polynomial of weight 2 in variables. So my conjecture based on 2 data points is that Ln is a homogeneous polynomial. Come on, my friend was an experimental physicist. They get 2 measurements right there, they get their normal price. Don't laugh at experimental physicists, they're smart, bunch of guys. Okay, so what do you do after you have L1 and L2? Oh, you try L3. Okay, so you try L3. So on 2 say, okay, what's L3? And we worked like a dog for this L3, nothing came out. Right? We didn't know what it was. And then in 2015, John Borwein, David Bailey, and Berkeley, and Crandall finally got to 15. They computed this thing to 1 billion digits, something like that. There's an algorithm called PSLQ that if you give him a decimal expansion, you give 100 digits of a number to this algorithm, and it tells you this is what this number could be with a high probability. This number is pi squared plus the root of zeta 7 and so on. 15 numbers, and they're always right. You give enough digits, the algorithm finds the formula. It goes the other way around, right? One knows how to go from an analytic problem, you do approximation, you get a decimal. This goes the other way around. It's tremendously surprising and tremendously effective. Okay, so this is the formulas. There's zeta 3, the famous a priori constant. There's pi squared. There's, look, weight 3 minus 2 is weight 1. This is also weight 1. This is A, whatever it could be, better have weight 1, because then this guy has weight 3. It turns out that the omegas are written here. This is omega 111. This means derivative with respect to the first variable, second variable, no derivative in the third variable. The omegas are called Tornheim. Tornheim was a Norwegian mathematician who did some papers in the 50s. Wrote one paper about this in the 50s. Then the subject disappeared, and then Witten said this could be interesting. So now they're called Tornheim-Witten zeta function. And there's a formula. The A has to do with this. There are derivatives and so on. I didn't write them down because it's hard to type. We have a similar formula for L4 involving this. Sometimes I say the calculation of L3 and L4 involve modular function. They really, honestly, I say modular because it's easy. Most people understand what a modular function is. These are really this convoluted zeta functions that Witten invented, that connected in a strange way to modular forms. We have no idea what to do with L5. No, I guess. I suspect for a long time that this has to be connected with modular forms in 2 variables. But this is just a suspicion. I have no idea what it could be. Okay, I want to tell you the minutes, how do we work? Okay, so sometimes somebody needs an integral for some reason, right? They find in the table. So this example, this formula here, I did not put a number. This formula appears in the table, right? It appeared in a work of this colleague of mine, Kim McLaughlin, and when he came to Tulane, we started talking about the different possible projects. And he said, look, we use this formula in something called, this is the famous KdV equation, right? KdV is one of these fantastic equations from the 19th century. You take UT, and this is like a wave equation, except there is an extra U there, making it non-linear. So the first 2 terms, if this U was a constant, this first 2 terms would be simply the wave equation in 1 dimension that you just move by translation, right? And then you have to, if this thing blows up with the U in there, right? So you don't like solution to blow up. So what you add is another term, and this is called a dissipation term. So you put the third derivative there in order to have the problem balance of the solution. If you start with a bounded solution, then it moves. Sometimes it changes, right? There are special solutions that they found out. They're called solitons. They come and they look like particles, right? That's why they're called solitons. And this was done essentially in the 1870s. These guys did not know then that they were doing algebraic geometry, but that's what the algebraic geometrists found this to their liking now. So they appears in lots of things like that. And so what Ken does is asymptotics of this equation. And the asymptotics appear in 5 different regimes. That's not important. He needed this formula to prove something with asymptotics. And when I was telling him the story that we found this error in the table, he said, wait, hold it. I used a formula, and he told me, I want to make sure that it's correct. Oh, it's you and I told him. So he came to ask me, how do you prove that? I have no idea. So this is the table. So the table's about this thick, right? So it's like 1,100 pages, right? So from the last edition we cut, there were like 50 pages of formulas with vectors. That we decided, completely arbitrarily, we just throw them away, these pages. Because nobody uses it. Like, somebody who wants to find a strange integral is not interested in finding formulas for the cross product, right? People complain, actually. People, the bad review on I don't know, on Amazon saying that they should not have taken the formula for cross product. You can't please everybody. Okay, so this is what we do. We are interested in improving this formula. So this is what it looks like, right? So if you've never seen this, is what the table looks like. This is the old editor, Dan Swillinger. My name appears inside, so for the next edition I negotiated that my name should be in the cover also. I do all the work, I better be there. So this is what it looks like. By the way, if you try using a symbolic language of this integral, with elliptic integral, Mathematica does not do things complex very well. Because one of the major open problems in symbolic computation is how to do contour deformation symbolically. How to transform a rectangle to a circle, nobody knows how to do it, symbolically, right? So, in an algebraic manner. So that's what the cover looks like. That's what the table looks like. It's too small, but you can see it. That's what the thing looks like. It's a dictionary. The tables, the formulas appear listed by more or less what they look like, what the integral looks like, right? Not by the answer, not by. On the right here, there are some reference to this table Beer of the Han, 1357. And if you go back to this table to look at this formula, most likely you don't find the right formula. Even these references are incorrect. So my plan is to make this electronic and to put it to this each. Nowadays, each of these formula has its own text document in which I put where they come from, what the proof is, why you're interested, and so on. I have lots and lots of empty LaTeX documents with just the formula, so I need help. So this is what the formula looks like. There's the one that we're looking for. So 42 appears, I forgot, maybe this one. I think it was this one here. Right? Oh no, this is the bottom. Doesn't matter now. Okay? So that's the one we're going to do. We found in the table, we want to figure out how to prove it. That's Ken, right? Thanks for asking. So after a lot of work, we managed to manipulate what we needed to prove about a formula for this series, right? And this series, if this Hn wasn't there, would be very nice, because that would be a hypergeometric function. Hypergeometric function means you take your coefficients and you divide two consecutive coefficients. If the series is geometric, the quotient of two consecutive ones is constant. Hypergeometric means the quotient of two consecutive ones is a rational function of the index. That's the definition. So it's a natural extension of rational function. So this thing is not hypergeometric because this also the bloody Hn. This Hn is there. Hn is a harmonic number. And if you divide harmonic n plus 1 divided by harmonic n is not a rational function of n. So this is a different kind of object. So we have to deal with this in a different way. So what I did was, first of all, there is John, my student. There's Ken, who got with the problem. There's me. And there's Teddy Ampedergan, who was my main collaborator. He was one of the first students of Doron Zalberger. And his office is next to mine. So I went to see, hey Teddy, let's play with this. I just gave him the formula first. I gave him this thing here. I said, I didn't tell him where it came from. Because Teddy doesn't like hypergeometric functions for some reason. So he played around and he found some methods and he was, yeah, this is very complicated. And then I had a postdoc some time ago named Christoph Kutschan, who's now a professor at RISC in Austria. Justino Peter Pauli, and he has a package for this kind of sums. And I called him, I said, Christoph, your package can do something? And he, after like a week, he said, yeah, it was really interesting problem. This is what the recurrence is. We put all the soup together, and there's the paper. Physical D. Collision of the shock region, KDD, and so on and so on. So this is more or less my modus operandi. I find an integral, and I found some people that I can convince to play with me. So be careful. Now you're gonna get emails from me. Okay, so I have 4 minutes. Yeah. Let me tell you, with this I'll finish. Okay? We have this is work that I've been doing for about 10 years now with a physicist from Chile. His name is Ivan Gonzalez. And his PhD thesis, he did a study of Feynman diagrams. Feynman diagram is also a very interesting source of integrals. Feynman, what he did was to take all this complicated interaction of particles and convert it to little pictures. And if you understand these little pictures, then you can understand the physics. I was explained. That's all I know about that. And then these little pictures become now an industry in many different parts of mathematics. They are interesting in many different ways. Right? What I want to show you is how this Feynman diagram generated the following type of argument. So you take a function, we call the method of brackets for a reason we'll come clear in 1 minute. You take a function in power series, I don't know what the radius is, not important, and I integrate term by term, right? So this is pre-Cauchy, right? Euler integrate like that, perfectly okay, and then this is good, right? So now you have to make sense out of this formula. So what you do is you declare that every time you get an integral with x to a power, you put a -1 there because the formula becomes simpler, right? And I call it something. But this is very much in the spirit of factorials. At the beginning of factorials, you multiply all the integers from 1 to n, you don't know what to do with them, you give it a name. You call it n factorial, now you make believe you know something about them. So this bracket A is the integral of this, right? Any real actually could be complex. It's not important. This integral is not well defined in any possible sense that you can imagine. Okay? The diverges of 0, the diverges of infinity, not important. So then you have an expansion. Whenever you have a linear expansion, what we notice is that in the integrals that come from Feynman diagrams, there's something called the loop expansion. In every integral, you always get power series that are linear in the index. So we have an expansion like this, right? And then you integrate term by term, and you get this. You get a sum of these guys. Yeah? So it's the linearity of the integral. The integrals diverge, not important. We need to decide rules and so on. Rigor, this is an irrelevant page. And then we have rules about how to convert a sum into a series of this type. We have a rule that says if you have a sum of r terms to an alpha, then you can replace it by a sum, not important right now, with a bracket there. And phi is what the physicists call a propagator. There are some rules. Here's rule number 1. Rule number 1 says, if you have an integral like this, a sum like this of brackets, you give it this value. Okay? So this is, Ivan invented this for his PhD thesis. You take this infinite series of things that are not well defined, okay, that's the number. He's a physicist after all. Okay? And n star that appears here is a solution of a linear equation. Solution of the linear equation appearing there. And then I started digging, trying to understand what this guy was talking about. That's my job in the collaboration, right? He says me things and I have no idea what he's talking about, and we talked about it. It turns out this is a theorem of Ramanujan. It's called the Ramanujan master theorem. And it requires to understand analytic continuation of a parameter and a wedge, lots of things, but that's not our business, not my business. Rule 3, it tells you what to do if you have a two-dimensional sum with two brackets. There it is, natural extension. Rule 4 says that if your system is not a square, then you do it over subsystems. And rule 5 says divergence answer, you discard them. This is the physics way. You do a computation, you get something divergent, you throw it away. Sometimes people now they call it renormalization theory. Give this guy a Nobel Prize, but what do we know? Okay. Can I have 2 more minutes? 2 minutes. It's 4:51. You can leave now, it's 4:51. Okay. Let me show you how to compute Wallace's formula. Wallace's formula is this. I write it like that. Right? Then I have this 1 plus x to an exponent. So the function 1 plus x to the minus n minus 1 gives an assignment of a bracket series. One bracket because the stuff's always in one bracket. You plug it in there, and you get that your integral is a two-dimensional sum with two brackets. I have a rule now. The rule is that if you have a double bracket, a double series, then what you do, you solve this 2 by 2 linear system. I can do that. You get this. So then you plug them in, and that's the answer. Okay, if you want to clean it up, you go somewhere, and you remember that gamma of m is n factorial. Probably there's a minus 1 there, type of number 10. And this gamma of n plus a half is this. You plug it in, you get the function. And that's it. Okay? And with this I'll finish. Thank you for listening, but I want to show you that these are the rules. They're all fit in one page. And it can be used not only for Wallace's formula. You take, if you like, Bessel integrals like that. Can be done all the way. Multidimensional. I was clearly more ambitious for this talk. Multidimensional. Easy integrals are really cool. They come statistical mechanics. There's a family of integrals. I was interested in this problem because anybody who works in this problem can do only 4 examples. We tried brackets and only 4 work. Something is going on here that we don't understand. And then you see that the answers are an L series and Z of 3, so there's number theory buried here that we don't know. Okay, thank you.
Questions for Victor?
I've been trying to sell this bracket method for a long time, right? So I gave a talk at Rutgers and I said, look, now the only thing we're trying to prove is to prove these rules. And who knows Doron Zalberg here in the audience? Have you seen Doron act in person? Doron is crazy, right? Completely crazy. He's my academic nephew, right? He said, that would be a waste of time. He said, the method works beautifully, there's no reason to do it. Yeah, so, proofs are overrated. So now we have all the proofs. We have all the proofs of the method. I have a paper written with rigor in case some editor one day to say, you have to prove this. Nah. I'll send it the paper, but it will never appear. So if you're interested, I will send it to you. But it will never appear. The beauty of the method is that computing every integral reduces to solving a linear system with very small number of variables. End of story. So, okay. Yeah?
Do you have a way of like classifying all the different like types of integrals that you want to compute?
I have a list of the ones that I can't.
Oh, okay.
I have a list of the problems that give me headaches. For example, this L5 that I have no idea what to do. I don't know, it's a classification. Classification things don't appeal to me too much. But I have lots of examples that I don't know what to do. So, yeah?
So now that you're keeping track of the motivation for why these integrals are interesting, if we ever in our research end up using one of these integrals,
Yeah.
do you want us
I
to
wanna
let
be
you know
called.
about it?
Huh?
Do you want us to let you know about it?
Of
so that
course,
you can
anything,
submit
even
your
if it
next
does, even
document?
if whatever integral appeals to you, send me an email. I have a huge folder with questions, more than I can answer. I try to reply saying thank you, because one of the things that we teach the graduate students when they come, I think it's very important that when somebody sends you an email, sends an acknowledgement that you got the email. It's not a tradition somehow. So anything that is interesting. There are integrals that have hyperbolic geometry computing volumes or things like that give you dilogarithm. Dilogarithm was a function that disappeared from the map since Euler until the 1970s. There was nothing on dilogarithm for 300 years, 200 years. And then it became super interesting. Right? So it's fashion. Yeah. It's important, as somebody says. Important meaning I like it. Yeah, so there's a very cool integral that I didn't mention. There's an interesting integral with both, it has the Riemann zeta function, the integrand, and it's equivalent to the Riemann hypothesis. So if you give an integral, somebody's not telling what to do, it's sort of unfair, but you never know. Yeah.
I have a quick question. In the entry you corrected, you had this function p, and it's a rational function. Is it unique?
Oh no, there could be other functions you can put in there to give the same answer, most likely.
Okay.
A vanishing integral for the rational function that, yeah. But I never thought of that, so that could be a good question. So.
Any other questions? All right, let's take a picture again.